Okay, do you hear me? Okay, Anurag, do you have any questions? Or do you want me to solve any problems? I have a book in front of me, so I can just do any problems from the book or answer anything. So today, to do maybe Stokes and Divergence curl. Any problems from the books that I have in mind? Okay, so let's maybe just practice with the Stokes Theorem and do one more for Stokes Theorem. And let's do something that we haven't done in class. And I see in the book it's a 16.8 problem 10. I believe it's going to be a good problem. And let's do the following problem. So what we have here. We have problem. Do you see this? No, let's see. Second. Try another marker. Is the okay? Let me find another marker. Give me a second. Okay, perfect. So problem 16.8, number 10. So we have problem 16.8, number 10. And for this problem, what we're given a vector field f of x, y, z. And f has the following form: 2y, x, z, and x plus y. So we have 2y, x, z, and x plus y. And what is my surface? Oh no, what's my curve? My curve is intersection of the plane. So my C described as intersection of the plane z equals y plus 2. And the cylinder x squared plus y squared equals to 1. And what I want to do, I want to relate the line integral over C of f dot dr. Okay, so I will give you just a couple of 30 seconds, try to think about this problem and set it up. Yeah, and this chapter number 16, basically is a whole chapter based on the idea that if you have the line integral over some curve C of f dot dr, then this integral is going to be equals to the double integral over S of n, when n is a unit normal vector of your surface S, of curl f ds. Yeah. And this, the whole thing, like this relation between a line integral and a double integral, is called Stokes theorem. Hi. So for the first part, what I want to do, let's compute the integral on the left-hand side. For first step, this C is not given as an equation, and C is not given as a parameterization. So we need to find this parameterization. Needs to find this equation based on these two equations. And these two equations telling you have two surfaces, and you can see how they intersect. You can reconstruct what is your parameterization is going to be. So the second surface is going to be just a cylinder that goes along the axis. So we have the following cylinder. But what about the first one? The first one, you can see you have just z to the first power, y to the first power, so it looks like it's going to be a plane. Like this, n, hat, or arrow, I believe is just notation, and the idea is just n just needs to be a unit vector. So we can put hat, put arrow. I can just erase everything. So to be honest, like I think it doesn't matter. Okay. And then what is my first surface? My first surface is going to be a plane. And it's really difficult to visualize and to draw a plane in 3D. But what we can do over here, we can see that in this plane, we have z and y. So it means if you will consider yz plane, then you can find when y equals to 0, z equals to 2. And when when z equals to 0, y equals to -2. So we have like this line. Y equals to -2. So it means since there is no x component, you will just take this line and trace it along x-axis. So here means if you will mention that your x-axis goes this direction, then you will have the plane intersect cylinder like this. So you can see that your curve is going to look something like this. And the book says that I want to choose there. When we use the Stokes theorem, when we have curve C, when you use parameterization, you need to choose orientation for a curve. And the standard one orientation for the given curve, like this curve is over C, is going to be counterclockwise. If you're going to look at this curve from the above, you just need to go into counterclockwise rotation. So in this case, you want to choose such orientation that we will go this direction. Okay. So for step 1, we're done, which can visualize our curve. So this is going to be my curve C. I don't have a color marker. So that's what we need to do for step 2. For step 2, we need to find the parameterization, and we need to find the right parameterization that it goes counterclockwise. So for step 2, let's find parameterization. So let's find, and parameterization in this case is going to be just, in this case, you can see R is going to be just R of t. Okay, so to find parameterization for this curve is not really difficult. If this curve will be in 2D, so in other words, if this curve is going to be just in xy plane, then you will have like a circle. And since x direction going to be this, x positive direction going to go towards you, then it means counterclockwise orientation going to look something like this. Yeah, it's okay. A second, here is a clockwise. Yeah, oh, sorry, this is the wrong orientation over here. Counterclockwise is going to be here, yeah. Because we want to go from y-axis into, from x-axis into y-axis. This is going to be my counterclockwise. Because if we will look, yeah, thank you, Narag. And for counterclockwise orientation, it's going to be the standard one. So your x component, you want to have cosine t. For your y component, you want to have sine t. Because when t equals to 0, you will get this point 1, 0. This is when t equals to 0. And when t equals to pi over 2, you will get 0.01. So every time if you choose an orientation, try to double check it, because sometimes people tend to do mistakes, so make sure that you choose the right orientation. Okay, we're almost done. So we know x, we know y. What about z component? And z component is going to be given by this equation. Because what I do right now with this curve, I kind of lifting up this curve into the curve that intersect with the plane. So you can see that when my t changes, my x component and y component are going to be the same, but t is going to change. So in this case, my z is going to change. My z is going to be equal y plus 2. So what I will have 2, and y is sine t, so 2 plus sine t. Okay, good. So we found our parameterization. And we just need to set our bounds. My bounds are going to be from 0 to t equals 2 pi, because I want to go around the circle only once. Okay, good. So we found our parameterization. Let's find the integral on the left-hand side. So step 3, let's evaluate the left-hand side. For the integral, for the left-hand side, we have it's line integral over C f dr. And here what I'm going to do, I'm going to expand my dr. But when you expand our dr, we know that if you have dr of t, it's going to be just equals r prime of t dt. Yes, but not only like r prime, because it will be true if my r of t is going to be a real valid function. So no, this is true. No, I need to explain this in a different way. I need to say like that my r of t is equals to x of t, y of t, and d of t. Yes, and then if I will find a d r of this one, I will have dr of t equals to. And here I'm using the fact that I said before. So dx of t is equals x prime of t times dt. So what I can see, what I will get over here, I will get x prime of t dt, y prime of t dt, and z prime of t dt. So this dr is going to be actually a vector, and f is my vector. So if I want to evaluate this integral, I want to find the dot product. But we can think about this dt to be a constant. Oh, you can see, sorry. But we can see like this dt to be equal to a constant. So what we can do with the constant in our vector, we can factor dt out. So we will have x prime t, y prime t, z prime t times dt. But for f, when we use parameterization, we're given f as this equation. We're given f as this vector function. So instead of y, x, z, we need to plug in our parameterization. So what we need to do, we need to find what is my f going to be in terms of t. So let's put here like star footnote. Let's find f in terms of t. And f in terms of t is going to be 2y, which in this case 2 sine t. And then 1 x times z is going to be 2 cosine t, cosine t times sine t. 2 cosine t plus cosine t sine t. Yeah, let's move it here. And the last one is x plus y, but x plus y is cosine t plus sine t. Cosine plus t plus sine t. And this is my vector f in terms of t. And okay, so here we'll need a lot of computation, a lot of space to compute. So let's put this r prime of t that I found over here. And what is my r prime of t? Because I want to find the dot product of r prime of f dot dr, and this is dr. So r prime of t is going to be just minus sine t, cosine t, and cosine t. Okay, perfect. So let me erase this. And let's compute left-hand side over here. So 3, left-hand side. Okay, let's check if you have any questions. This is not f of prime, no. This is just f of t. So, and then you can see left-hand side. So what we just did, we choose our orientation on my curve. I found parameterization, and I found the r prime of my parameterization, and I express f in terms of my parameter. So right now what I need to do, I just need to relate this integral. So I have integral c of f dot dr, and when I'm going to put everything in terms of t, my bounds going to be correspond to the change of t. And since t changes from 0 to 2 pi, then my integral is going to be from 0 to 2 pi. And the next thing, I just need to find the dot product of these two. So the dot product of the first component is going to be negative sine square t plus. Here we'll get plus 2 cosine square t plus cosine square t sine t. Yes. And the last one, yeah, we'll have plus cosine square t, because I'm multiplying this one, plus cosine let's put it here, plus cosine t, cosine square t sine t. Okay. Oh, I don't like this integral. It's too long. Okay, so first of all, let's check, did we do any mistakes? 2 sine t. This is no mistake. Cosine t sine t. Okay. Derivative, derivative, derivative. Okay, so I feel negative 2 sine squared. Okay, so can we simplify anything here? Yeah, but in this problem, we will ask compute the integral on the left-hand side. We will ask to compute this integral. So what I'm going to do, I will compute the integral on the left-hand side, and then we're going to do computation on the right-hand side, and we will see what we will get. Okay. So here, let's check if we can simplify something. I believe no. So let's just rewrite my integral. I will have integral from 0 to 2 pi. We have 2 cosine square, and we have cosine square t. So what I'm going to get? I'm going to get 3 cosine square t. Then I have minus 2 sine square t, minus 2 sine square t. And I have cosine t sine t and cosine square sine t. So plus cosine square sine t and plus cosine t sine t dt. Okay. Okay. Let's evaluate this integral. Okay, let's try to cheat. And by cheating, I mean because we have integral from 0 to 2 pi. So, yeah, so we know that if in our answer you will have sine function, then that integral is going to be equals to 0, because sine at 0 is 0 and sine at 2 pi is 0. Let's take a look at this integral. This integral is going to be just 1/2 sine 2t. I use here trigonometric formulas that 2 cosine t sine t equals sine 2t. But integral of this one is going to be cosine, so we have no problem. So the last term is not going to be 0. So let's just write the value for this integral. I will have 1/2 cosine 2t over 2. Yes, because if you will, and minus sine. Okay. So I have negative cosine. I will integrate this one, and I will get sine 2. 2 will get cancelled. Okay, perfect. And this is my from 0 to 2 pi. Okay, yeah. So this one is going to be 0 because I will factor my minus sign over here. And then cosine at 2 pi is going to be 1, minus cosine at 0 is also 1. So the whole thing is going to be equals to 0. So this integral is going to be plus 0. Okay, yeah, perfect. This one, we can use kind of really fast computation. Here I'm going to use u sub. And what u I'm going to use, I'm going to u equal cosine t. So du is going to be negative sine t dt. So we'll have minus sign over here. So when I will use u sub, this integral cosine will become u squared. So when I will take my integration, I will have u cubed over 3. But my u is going to be cosine t. So actually what I will have cosine cubed t over 3. And this changes from 0 to 2 pi. So what I will get in this case, you can see that negative cosine of 2 pi equals to 1. So we'll have 1/3 minus cosine at 0 is also going to be 1/3, also 0. Okay, so this term is also 0. Yes. Cosine 2 pi is 1, and cosine at 0 is 1. 1 minus, oh yeah, it's 0. Yeah, thank you. So you can see even this integral doesn't look nice, we already have, with like relatively fast, we computed that these two terms are 0. Let's check this term. And this term, I believe we have already computation. Or no? Yeah, for this one, we can just use, okay. Here I can, let me think. I can a little bit simplify this computation. If I will subtract sine squared t and add sine squared t, and I'm going to add here sine squared t, then this term by another trig identity. If I will factor 3, I will have cosine square minus sine squared t. It's equals to cosine 2t. So cosine squared t minus sine squared t equals to cosine 2t. But when I will integrate this, I will get sine function. And sine function from 0 to 2 pi is also 0. So it means this term is also 0. So the only terms what's going to be left after like this crazy computation is going to be left the integral from 0 to 2 pi of sine squared t dt. But as it already said in comments, sine squared t is going to be just integral from 0 to 2 pi. And here I use another trig identity. It's going to be 1 cosine 2t dt. But I always forget, is it minus or plus? But one way is, remember, if like this left-hand side equal to sine squared t, you multiply by 2. When you expand your cosine squares, cosine squared t minus sine squared t, we want to cancel out one of the sign. And the way how we're going to cancel out over the sign, if we're going to have minus sign, because we will have sine squared t on the left-hand side equals 2 sine squared t on the right-hand side. And by the same reasoning over here, this integral will give me 0. So the only what I'm left 1/2 t from 0 to 2 pi. So it equals to pi. Oh, damn. Okay, so we got the left-hand side is equals to pi. So let's put this value over here. So my left-hand side equals to pi. Okay. Okay, so we compute the left-hand side. And I wish not you to get this problem in meter, because this problem is not bad, but just computation part can be misleading. So let's do step number 4. This problem didn't ask us to find the integral on the right-hand side, but let's find the integral on the right-hand side and see if we did mistake. Or if I did mistake, because I did all computations. So right now I want to evaluate this integral. But the question is, what is my s? Because in this problem, I'm not giving any s. In this problem, I am giving this my shape of cylinder. And for the cylinder, I have, this is my curve C. No, wrong orientation. So by Stokes theorem, as you see in the picture, we have some curve C with converse orientation, and then we attach some kind of cell, some surface. And this cell or the surface we called S. So you either find the line integral over the C, or you find the surface integral over your surface. For this case, let's just make our life easier. Let's take the surface to be equal the disk enclosed by this curve C. So this is going to be my S. Okay, and let's try to relate this integral. So what I need to do, I want to find the double integral of S and curl F ds. And here's a couple of steps. So first, I need to find what is my curl F. So let's find curl F. If you don't understand the meaning of curl, because we know how to find the curl, or you want to see what is the intuitional definition of curl, let me know, because I can just give you a couple of examples, and after these examples, you will understand what does curl mean. Usually, NRUG, you given what is your S. But in this case, I just want to choose any S. Because the point is, if you have the line integral, if you have the surface integral over the line, for example, when we have for this problem, then it doesn't matter what surface you're going to choose, you're always going to get the same answer. Yeah, it's the same as boundary as C. Yeah. This is basically the idea and the beauty of the Stokes theorem. Okay, so we have this curl f. And in this case, my curl f is going to be partial derivative of y. So we'll have 1 minus partial derivative of z minus x. My y component, partial derivative of x with minus, so we'll have minus 1. Partial derivative of z, and z is 0, so it's going to be minus 1. And the last component, partial derivative of y, 2. Partial derivative of x, z. So we'll have z minus 2. Okay, so curl is not bad. The second part, I need to find what is my normal vector. So we all know how to relate the surface integrals. We have 3 approaches. We can either use parameterization, partial derivatives, or gradient. Yeah, it's super cool. In this case, I can find my normal vector by using gradient, because I can see that my surface is just a plane. So for the plane, my gradient is going to be a normal vector. But I want to be this normal vector be unit 1. So I will extract my gradient by I will extract my unit normal by taking the gradient of this function. And we can see that the only thing I need to choose a positive orientation, yes, because when I go counterclockwise, let me draw a picture. I want to be my normal vector be this direction. So from this, the best way to do this is to draw a picture. So we have, this is my y, z equals y plus 2. So the gradient of this function is going to be z minus y equals to 2. So I will have 0, minus 1, and 1. And let's check it's going to be actually pointing this direction. If I will be at this point, I need to go minus 1 in y direction and plus 1 in z direction. So I will have this vector. Okay, so this is my normal. So my normal is 0, minus 1, and 1. But I want to be this a unit normal, so I need to divide by magnitude of this vector. So in this case, I will get square root of 2. So my unit normal vector is going to be just 0. No, let's just keep it this way. And the last part, so what we did, we found our curl. We have my n, and what is ds? And ds, we know that is surface area unit. And we want to express this unit of surface integral unit. And we want to express as a surface unit of the in xy plane region. And we have a couple of formulas. Let me just write to you all possible. So we have either magnitude of RU cross R of V of my parameterization dA, or it's going to be 1 plus z of x partial squared plus z of y partial squared. So in this case, what I will get dA. And we can see that we didn't use any parameterization here in terms of surface integrals, and we use for gradient partial derivatives, so it means it's easier going to be just like partial derivatives. So in this case, I will get that my ds, let's put it over here, my ds is equals to 1 plus 0, partial of this one is going to be also 1, equals square root of dA. Okay. So we got all our information for the integral on the right-hand side. So let's just evaluate this integral. So we'll have the double integral n dot curl. So when I'm going to dot them, okay, first thing, you have square root on the bottom over here, and you have square root on the top over here. So these square roots are going to be cancelled. And this is actually true for any integral. Yeah. And the next thing, when I will find the dot product of curl and n, x is not surviving, so surviving only y and z. So that's why we'll have positive 1 plus z minus 2. And this whole thing is going to be just dA. And right now I have integral over d. So what I did over here, by taking the surface area, I dropped it to the double integral over this region D in xy plane. But when I dropped it, I changed my region by this factor, and this factor is called Jacobian. So right now what I'm doing over here, I'm just evaluating the double integral over a scalar function. And to do this, we need to describe our region D. But we can see when you're projecting that thing into xy plane, your D is just going to be x squared plus y squared less or equal than 1. So it's going to be a circle. And every time when we have a circle, what we want to use? We want to use polar coordinates. So here, let's use polar coordinates. Here's one thing. Okay, so can you spot a mistake over here? Let's just, I'll just want to kind of do a small quiz. So what mistake do I have over here right now? And Rag, what do you think? It's not big mistake, but it's kind of important mistake. Yeah, the mistake is when we have the double integral over region in xy plane, the function inside that goes over here, it's f in terms of x and y. So I cannot have variable z. But z minus 2 is equals to what? Is equals to y. So here I will have 1 plus y. Okay. So every time when you stop integral over the plane, make sure that you have your integral in terms of components of your region in the plane. So I have 1 plus r sine theta, because it's polar coordinates, times r. And here I have dr d theta. And theta changes from 0 to 2 pi. R changes from 0 to 1. Yes. And let's avoid this integral. So what I will get over here, okay, let's erase, what do you want to erase? Maybe let's try to move camera, or not. Yeah. So what do we have over here? Unfortunately, I cannot split into some of the two integrals, so let's do this, how this integral should be done. So I have integral from 0 to 2 pi. Then I will have r squared sine theta. So I have r squared over r over 2 plus r cubed over 3 sine theta. R changes from 0 to 1 d theta. So over here I will get for this thing from 1 to 0, so I'll have the double integral from 0 to 2 pi. When 0, these two terms are going to be at 0. When 1, I will have 1/2 plus sine theta over 3 d theta. This is from 0 to 2 pi. And we already done this computation. Okay, I'm going to put it over here. So we can see that I will have integral 1/2 t from 0 to 2 pi, but this integral is going to be just equals to pi. What about second integral? The second integral is going to be just negative cosine theta over 3 from 0 to 2 pi. But this integral equals to 0. This integral equals to 0. So the whole integral on the right-hand side equals to pi. And we are done. So what we did over here, we computed the integral on the left-hand side, we will get pi, and we computed integral on the right-hand side, and we also got pi. And this is power of the Stokes theorem. I don't know in this case what integral were easier, integral on the left-hand side or right-hand side, but I wanted to show you at least one computation for the problems that I haven't done in class. and I believe this was a good problem. So let me know if you have any questions. And if you want me to solve any other problems or explain divergence, curl, okay, so what is this? Do we have any good problems in the book? When 2 plus 2 doesn't equal to 4, let 4 equals 5. 2 plus 2 doesn't equal to 4 in Z mod for Z algebraic like ring. So if you have, you can think about like if you have a numbers like real numbers, or like let's say natural, like let's take real numbers. This list of numbers represented by a line, and you have subset natural numbers of real numbers, and n. No, let's not n. Let's take z. Let's take z, and these go 0, 1, 2, and you go in negative direction -1, -2. So, and this is your real line. So this is your z. So z is just going to be dots on a real line. So what does z mod 4 mean? It means instead of taking this line, let's take 0, 1, 2, 3. But when you're going to have number 4, you will have 0. And what does it mean in this picture? It means you can think if you will have just this kind of road, then you will make a circle. You will take the 0 and will rotate. So for z, the corresponding like geometric picture is going to be the real line, then for z mod 4z is going to be a circle that looks like this. So we have 0, 1, 2, 3, and this is going to be 4, 5, 6, and 7. But let's come not to worry about this, because what you did with this line, you just wrap this around the circles infinitely many times. And that's why if you will take 2 plus 2, in this case, so we have 2 plus 2. So in this, it means I need to go 2 counterclockwise and 2 again clockwise, you will get 0. 0. And 0 doesn't equal, it doesn't equal to 4. It doesn't equal to 4, let's say this way. It doesn't equal to 4. Because there is no 4, first of all, but this is one of the examples. Okay, let's say this way. When we have 2 plus 2 equals to 4, 4 is non-zero, 2 and 2 is non-zero. So both parts are not 0. Yes, but here 2 plus 2 is going to be equals to 0. Yeah. So this you can call like infinite arithmetic, and this is finite arithmetic, because here if you will take number 1 and you will add this number 1 like two times, 3 times, and you multiply n. If you multiply n by 1, is never going to be 0. Except when n equals to 0. But in this case, it will have 1 plus 1 is 2, 1 plus 1 plus 1 is 3, 1 plus 1 plus 1 is like 0. So for this circle, you can see that we have 4 times 1 equals to 0. And in this case, your n is equals to 4. Yeah, and this is abstract algebra. This thing is called the order of your element. So in this case, we're saying that order of one is 0. Why it's 0? Because when you go in any direction, you're always gonna get, you're never gonna get that n times 1 is going to be equals to 0. So, but in this case, order of my 1 is going to be 4. Because if you multiply by 4, or like add 4 times, you will get 0. So like order of some element is a minimum integer such that n times 1, let's say n times a doesn't equal to 0 except n equals 0. Okay, do you have any other questions? Yeah, it's not Stokes theorem, but it's also cool. Okay, do you have any other questions? Okay, so I was booking this room till 10 a.m., so I need to go, unfortunately. If you want me to, I'm going to do another online session and we're going to discuss practice finals problems next week, because I checked the final and the final is pretty hard, so I want to make sure that we're going to go over the final. And that's it for today. I hope you enjoyed this video. So if you're not subscribed, then subscribe. Is probability that a quadric at least? Yeah, I'm gonna go online because people are kicking me out from the study room. So okay, see you. Thank you. I need to smile more.